Hello, my name is Savannah Saucedo, and I will be presenting Team 2's Ceres Sample Return Mission. The topics of this presentation include mission overview, mission requirements, modeling assumptions, technical calculations and analysis, launch vehicle and spacecraft specifications, phases of the mission, full simulation, alternative mission plan, and finally the summary. The team designed a Ceres sample return mission, which would allow a sample to be retrieved from the locator and data to be relayed to Earth over a period of 6 years, 7 months, and 5 days. A spacecraft will depart from Earth, rendezvous with Ceres, descend and collect samples, and finally return safely back to Earth. The mission requirements are as follows. Launch date between 2025 and 2030, the duration of mission less than 15 years, V infinity at the Earth's sphere of influence of return trajectory to be less than 10 kilometers per second, and the orbit altitude to be around 50 kilometers over the landing site selected. Why Ceres? Ceres is a water-rich body and the only object in the asteroid belt known to be rounded by its own gravity. It is critical to learn about the formation of Ceres. The team designed the mission using the JPL Horizon system to obtain the positions of each significant body. Using MATLAB and FreeFlyer, the team was able to calculate the necessary information to obtain the optimized trajectory path to Ceres. The team made the following modeling assumptions in order to begin the design. The spacecraft will not travel below 0.6 AU with respect to the Sun, and the landing site reconnaissance orbit around Ceres will be near polar and sun synchronous. Two pork chop plots were made in order to determine a launch date with an adequate deliverable mass and the C3 of the launch vehicle. From these plots, a launch date was chosen that would give a deliverable mass of 2,093 kilograms and a C3 of 76.787. The launch vehicle selected with this C3 had a launch mass capability of 2,460 kilograms, which was greater than the payload mass of 2,055 kilograms the launch vehicle was used to deliver. A third pork chop plot was produced to determine a departure date from Ceres that would provide a V infinity to less than 10 kilometers per second. This was a requirement for this project in order to ensure a feasible Earth entry trajectory. From this plot, a departure date that would give a C3 of 43.63 was selected, which corresponded to the V infinity 2 of 9.673 kilometers per second. The launch vehicle that was chosen is the Falcon Heavy, which requires a total propellant mass of 77,311 kilograms. This launch vehicle was chosen from the NASA Launch Service Program, with the C3 determined in the pork chop plots that were previously shown. The team selected two propulsion systems, one for the spacecraft, another for the landing ascending module and the return capsule. The NASA Evolutionary Xenon Thruster was chosen as the propulsion system for the spacecraft due to its high ISP. For the landing ascending module and the return capsule, a liquid oxygen, liquid hydrogen propulsion system was selected. These two propulsion systems were chosen to ensure the lowest propellant mass required for the mission. The payload consists of a spacecraft, landing ascending module, and a return capsule. The dry and propellant mass is listed below for each component. The mission will begin with a parking orbit around Earth. The initial mass of the spacecraft is 2,055 kilograms. On January 25, 2028, the mission to Ceres will commence. A delta V of 9.2191 kilometers per second is required to leave Earth's orbit and send the spacecraft onto the optimized trajectory path to the dwarf planet. The total amount of propellant needed to execute this maneuver is 77,311 kilograms, and the time of flight is 223 days. In order to be captured in a polar orbit around Ceres, a delta V of 3.4955 kilometers per second is required. The low-thrust propulsion system of the spacecraft will provide this delta V in an estimated time of 348 days. On September 15, 2029, the landing ascending module and the return capsule will separate from the spacecraft and land on the locator. It will remain at this location for the next 6 years, 7 months, and 5 days. During this time, it will collect samples from the locator and relay information from the spacecraft back to Earth of Ceres environment. On April 20th, 2036, the ascending module and return capsule will ascend to the spacecraft orbit altitude while leaving the landing module on Ceres. The return capsule will then separate from the ascending module and rendezvous with the spacecraft. On March 11th, 2039, the spacecraft's propulsion system will provide a delta V required to return to Earth in 468 days. The delta V's required at each phase of the mission are summarized here. A visual of the mission final design is shown here. An alternative mission design that includes a Mars flyby in order to reduce the required delta V is shown here and in the following slide. The trajectory optimization tool on MATLAB was utilized to create these optimized routes. The total mission time was 14 years, 11 months, and 29 days. During this time, the landing ascending module and return capsule relayed information to Earth of Ceres environment and successfully retrieved a sample of the locator.